Assalamu alaikum, welcome back class. So this is our first lecture of the electronic devices and circuits. So we started this lecture, okay, and we learned about the importance of the semiconductor materials for the fabrication of the different kind of electronic devices. For example, resistor, capacitors, op-amp, ICs, integrated circuits, transistors, and they are being used in a wide range of applications. Like every digital circuits, whatever we are talking about, like for example the motherboard of your computer, the Android mobile phones, okay, anything, okay. So the electronic semiconductor devices are being used everywhere, and we learned about the difference between the conductor and insulator and semiconductor. So conductors are the materials from which the flow of current, flow of charge is possible, and insulators are the opposite of the conductors. So the common example of the conductors are the copper, aluminum, steel, or any metal. Okay, insulators like the anything by which the charge cannot be flow. So plastic, rubber, glass, cloth, wood. Okay, these are some examples of the insulators. Semiconductors are the materials which are actually lying in between the conductor and insulator. So like conductor, insulator, and here we have the semiconductors. And the common examples of the semiconductor materials are silicon and germanium, and we have discussed this thing in quite details. The properties of the materials are defined by the conductivity or resistivity of material. So resistivity of the material, we usually represent resistivity using rho and conductivity using sigma. So sigma is the 1 over resistivity. So conductor will have the uh, lowest resistivity. Okay, resistivity, this is the resistivity value for the copper. Okay, so the conductor will have the lowest resistivity, means it will have highest conductivity, and insulator will have the highest resistivity, means it will have lowest conductivity. Conductivity defines the flow of charges, that how easily the charges can flow through a material. That is actually defined by the conductivity of the material. So semiconductor lies in between them. Okay, like typical value is around 50 ohm for the germanium. Then we discuss about the structure of our atoms, because we want to learn about the inner configuration of the semiconductor materials, how semiconductor materials are formed. So before going into the details of those, we learned about the basic configuration of an atom of a metal. Okay, so atom have nucleus. It has three different charges: electron, proton, and neutrons, which are revolving around the nucleus in the different shells. So the electrons which are near to the nucleus, they have a stronger bonding. Okay, for example, this electron, it will have a very strong bonding. Because electron and positive charges, like negative and positive charges, will attract each other, so they will have strong bonding. So the outermost shell is also referred as the valence shell, or the electrons here, they will be referred as the valence electron. So these valence electrons, okay, they will have a relatively lower bonding with the nucleus, because they are away from the nucleus, okay, as compared to the electrons which are near to the nucleus. Okay, so valence electrons have lower bonding, okay, but they have highest energy. Okay, highest energy. These electrons will have the highest energy, because they are away from the nucleus. Okay, so for the conduction of the charges, for the conduction of, like for current, voltage, we need the free electrons. Okay, so usually the like the electrons are bounded with the nucleus and they are revolving in different shells. Okay, so to get the free electrons, okay, we actually have to remove the electrons. Okay, and the easiest way is that we remove the electrons. Remove the electrons means we want to remove the bonding of the electrons with the nucleus. okay, because the outermost shell has lowest bonding, okay, it's easier to release them from these shells, from the valence shells, okay, and once they are removed from the valence shell, okay, they will go to, sorry, they will go to another outer shell, which is actually called conduction band. So once the electrons are in conduction band, they are free to move, and they will be actually playing a role for the movement of the charges, okay. So we actually require an external source. We require an external source so that we can remove these valence electrons, okay, and make them go to the conduction band. So the requirement of external energy it will depend upon that how much that what is the bonding of the electrons with the nucleus. If they have lower bonding, we would require lower energy for the release of the electrons. If they have tighter bonding, we will require more energy, okay, for the release of those electrons, okay. So how much energy is required, okay, to move the electrons from the valence band to the conduction band? This is actually referred as the band gap energy. So this defines that how much energy we require, okay, so that we can remove the valence electrons, okay, from the valence band to the conduction band, okay. The stronger the bonding of the valence electrons with the nucleus, okay, the higher energy would be required. The lower the bonding of the valence electron with the nucleus, the lower band gap energy will be required. So the band gap varies. Band gap, the requirement of this energy varies from the different materials, okay. So you can review this, that like why like we are having the high band gap energy for the insulators. So because in the insulators the electrons are more tightly bounded with the nucleus, so we will require highest level of the band gap energy, okay. For the semiconductor, this band gap energy level will be lower, and for the conductors this is almost like 0 evolved, okay, because like in the conductor we have like even at the room temperature, like if we get a little bit of energy, okay, the electrons will move from the valence electron to the conduction band, and the flow of charges, the flow of current will start, okay. However, like in the insulator, okay, because there are more stronger boundings, okay, we will require a large amount of the band gap energy for the movement of the electrons from the valence band to the conduction band. So this is a slide showing the difference between the atomic structure of the semiconductor and conductor atoms. So this is a silicon atom. Okay, so in silicon atoms we can see that the core, okay, the core of the silicon has a net charge of +4. Okay, why it is having a net charge of +4? Because silicon atoms have 14 protons, okay, and if you count the number of electrons, okay, so the number of electrons in the core, so if you remove the valence electrons, the all other things is referred as the core, okay. So 1 2 3 4 5 6 7 8 9 10, okay, so there are 10 electrons in the core and 14 protons. So 14 protons minus 10 electrons, we will have the net charge of +4, okay, and we have the 4 valence electrons here, okay. And here we have the 3 shells, 1 2 and 3 shells. Now let's look at the copper atom, okay. In the copper atoms, okay, we are having 29 protons, okay, and if you count the number of electrons in the core, they are 28, okay. So basically the net charge, okay, is 29 minus 28 plus 1. So the core have a net charge of +1, okay, and there is only one electron in the valence shell, okay. And here if you can see, we have 4 shells, 1 2 3 and 4 shells, okay. So the first thing is in semiconductor materials, okay, we can see that the net core charge is +4. Here the net core charge is +1. So this is +4 core charge is more stronger as compared to the plus 1 core charge. Okay, it means electrons here, okay, they have stronger bonding as compared to the electrons here. Okay, number one. Number two, if you see that here we have only three shells, okay, 1, 2 and 3. So these valence electrons, these are 4 valence electrons, okay, they will have stronger bonding with the nucleus as compared to this valence electron because it is in fourth shell. So as we move away from the nucleus, the bonding will be reduced. Okay, so these valence electrons will have lesser bonding with the nucleus, okay, as compared to these valence electrons, okay, because they're in third shells and this is in fourth shells. Okay, so the overall it is easier to remove these valence electrons, okay, in the conductor as compared to the semiconductor material. That's why even like at the room temperature, okay, the supply of a little bit of energy will let the flow of the electrons in the conductor items. Okay, so this is a difference between the semiconductor and conductor items, and that is the reason why, like for the semiconductor material, okay, we need higher band gap energy, and for conductor we need lower band gap energy because of the lower bonding of the valence electrons with the nucleus and the lower net core charges. So we have like seen the difference between the semiconductor and the conductor material. Okay, so let's see what is like if we have the same kind of the semiconductor materials, then what will be the difference between them. Okay, so we are comparing silicon and germanium. Okay, these are the most common semiconductor material used for the electronic devices. Okay, so this is the atomic structures of the silicon, and this is the for the silicon like we have seen earlier, and this is for the germanium. Okay, in the case of germanium, okay, we can see that there are total 32 electrons here. Okay, like the 2, 8 and 16. Okay, right. So in the core, okay, we have net the core, because we know that this all is core. Okay, these are the valence electrons, so we have 32 electrons in the core. Okay, and there are 4 electrons in the valence shell. Okay, so how many number of shells we have here? Okay, let me write the number of shells here. So this is first shell, this is second, this is third, and this is the fourth shell. In silicon, first, second and third. Okay, so the number of electrons in the cores are 8 plus 2, 10 for the silicon, and for the case of germanium we have the core electrons of 32. Okay, there are 4 shells in germanium, and there are 3 shells in the silicon. Okay, both silicon and germanium have 4 valence electrons. You can see that. Okay, 1, 2, 3, 4, 4 valence electron here, 1, 2, 3, 4, 4 valence electron here. Okay, both silicon and germanium have 4 valence electrons in the valence shell. Okay, but the valence electrons of the silicons are in the third shell. The valence electrons of the germanium are in the fourth shell. Okay, so the valence electron of the germaniums, okay, they will have lesser stronger bonding with the nucleus, with the core, as compared to the valence electrons of the silicon, because they are in third shell. So the third shell will have the comparatively stronger bonding of the valence electron with the nucleus. Although they have the same number of valence electrons, okay, their bondings will be different. So as we like move from one semiconductor material to another material, okay, the characteristics in the bonding of the electrons with the nucleus, that defines the requirement of the band gap energy. Okay, now for example, if we compare the band gap energy of the silicon and germanium, so for the silicon we would have higher band gap energy. Okay, for the germanium, okay, although they have same number of valence electrons, okay, we will require the lower number, comparatively lower band gap energy. Okay, so far we have seen just the structure of an atom. Okay, but the actual material, okay, there are large number of atoms which are bounded together. Okay, which are bounded together, and then it actually make an material or metal or semiconductor. Okay, so basically that pattern, the bounding, okay, finally is called crystal. Okay, and the periodic arrangement of the atoms is usually referred as the lattice. Okay, the bonding of the large number of the atoms together is actually form the crystal of the actual semiconductor or the metal material. Okay, so this is so far we have learned about the importance of the valence electrons, the core charges, and the band gap energy. Requirement of the band gap energy, that how much external energy we would require for the releasing of the valence electrons to the conduction band to start the flow of the charges. Okay. The next topic is we are switching towards the from the atom to the metal level. Okay, so as I said earlier, okay, in the actual matter there will be a huge number of the atoms which are bounded together. Okay, so what will be their bonding look like? Okay, let's say this example. This is a crystal of the silicon or germanium. Okay, whatever you think. Why? Because in both cases we have the 4 valence electrons. Okay, like we have seen here. Okay, in both cases, okay, we are having the 4 valence electrons. So what is actually happening? For example, this is the silicon. Okay, this is silicon, another silicon atom, this is another silicon atom, and this is another silicon atom. So this silicon atom have 4 valence electrons. Okay, like this, and this, and this. This is the second atom, and so far third one. Okay, so basically these valence electrons, okay, and these valence electrons, okay, they will form a bonding with each others. Okay, so this bonding is actually called covalent bond. Okay, so basically in other way we can say that the neighboring atoms, okay, the neighboring atoms will share their electrons. Okay, and eventually that sharing, okay, will results in the covalent bond. Okay, so this covalent bond is actually holds the atoms together. Okay, so different atoms will be bounded. Okay, and that bonding is referred as the covalent bonding, and that holds the atom together to form the actual semiconductor matter. Okay, so this is the way that how the actually atoms are formed. Okay, so we learned about the semiconductor material, we learned about the structure of the atoms, we learned about the difference between the semiconductor and the conductor material atom, we learned about the difference between the atoms of the semiconductors like silicon and germanium, and we learned about the covalent bonding. Okay, now let's have a look some more details about the semiconductor materials. Okay, so semiconductor materials can be categorized into 2 things. Okay, intrinsic and extrinsic. Okay, intrinsic. So okay, so we can categorize into 2 categories: semiconductor material, intrinsic and extrinsic. Okay, intrinsic are the pure semiconductor materials. Okay, pure semiconductor materials. Okay, extrinsic are the opposite of the pure semiconductor materials. Okay, so what does meant by the pure semiconductor material? So we have seen that, for example, silicon and germanium, okay, both have 4 valence electrons, right? Okay, so now and we have seen that the conductivity of the semiconductor material lies between the conductor and insulator. Okay, but we want to use the semiconductor material for the flow of charges. Okay, so we can actually alter the characteristics of the semiconductor materials. We can change their conductivity and resistivity properties. And how we can do that? We can add other materials, other atoms in the pure semiconductor materials. Okay, for example, there is one silicon atom. Okay, and we know that silicon atom will have the 4 valence shell electrons. Okay, so we can add another atom. Okay, and that addition of that atom would change the characteristics of this structure. Okay, would alter the resistivity and conductivity properties. Okay, so when we add another atom in the pure silicon, okay, it will become extrinsic semiconductor material. Okay, so intrinsic are pure, okay, like only silicon, germanium. Extrinsic are the addition of the other metal to change the characteristics of the semiconductor material, because generally overall semiconductor materials are poor conductors, so we want to increase their conductivity, and for that purpose we add other items in them, and that process is actually called doping. Okay, doping is the addition of the other electrons, okay, and that will make the semiconductor material extrinsic semiconductor materials. Now the question is, okay, what kind of atoms we can add, okay, what kind of atoms, what other items, also we call them impurities. Okay, okay, so impurities, okay, it could be pentavalent material, okay, or trivalent. Pentavalent material means they will have 5 valence electrons. Okay, trivalent materials, they will have 3 valence electrons. Okay, so if you add pentavalent material like antimony, phosphorus or arsenic, okay, in the silicon materials, okay, its characteristics will be changed. If you add a trivalent material, its characteristics will be changed, okay, and this process is called doping. And now let's see how the characteristics will change. Okay, for example, we have a silicon atoms here, okay, and we know that silicon atoms, okay, we have the 4 valence electrons. Okay, so these are the valence electrons, 1, 2, 3 and 4. Okay, these are the valence electrons of the silicon. Okay, so every silicon atom have 4 valence electrons. Okay, so we added the impurity, which is antimony, which actually have pentavalent, okay, valence electrons. This is a pentavalent material, so it means it will have 5 valence electrons. 5 valence electron means, okay, so silicon has 4 valence electrons, it will have 5 valence electrons. Okay, so we can see that like 1, okay, 2, 3, 4. Okay, so these 4 valence electrons of the antimony, okay, they will form a covalent bond, okay, with the silicon atoms. Okay, 1, 2, 3 and 4. Okay, so the 4 valence electrons of the antimony, this pentavalent material will form the covalent bond. Okay, so but it has 5 valence electrons, so we will have 1 free electrons. Okay, after that adding of this impurity. Okay, so the overall what we are getting, okay, we are getting the free electrons in the overall structure of the materials, okay, by adding a pentavalent materials. Okay, so basically when we get more free electrons, okay, free electrons means or negative charges, so higher the number of negative charges, okay, it will be higher the number of the conduction band electrons. Okay, so it increases the overall the number of the conduction band electrons. So as we are having the more free electrons, okay, so such kind of materials are actually called as n-type semiconductor materials. Okay, so when we add pentavalent material impurity to the pure silicon extrinsic semiconductor material, okay, we will have the free electrons, and such construction is called the n-type semiconductor materials. Now let's look at the opposite. If you add a boron is a trivalent material. Trivalent material, it will have 3 electrons, valence electrons. So these 3 electrons will have the covalent bond, okay, with the other silicon atoms. Okay, so we will have but we know that silicon atom have 4 valence electrons, right? 1, 2, 3. Okay, so due to this, okay, because it have 3 valence electrons, so now a hole will be created. Okay, now a hole or a positive charge will be created. Okay, so when we add a trivalent impurity, okay, so that will create a hole. Okay, because you have an electron, so electron will be actually attracted towards the towards the positive charges, proton. Okay, so the addition of the trivalent material will create a hole in the crystal of the atom. Okay, so now we are having the hole means positive charge. So such kind of semiconductor materials are called p-type semiconductor materials. So we have seen two kinds of the semiconductor materials, p-type and n-type semiconductor materials. Okay, in the n-type semiconductor materials we have more number of the free electrons. Okay, so and lesser number of the holes. Okay, so basically majority carriers, okay, majority carriers here, there will be free electrons, and minority carrier. Minority carrier means the charges which are actually carrying the currents, charges. Okay, so the minority carriers will be hole holes. Okay, because we have a high number of the free electrons here, and the opposite will be for the p-type semiconductor material. Here the majority carrier will be hole, and the minority carrier will be electrons. Okay, so basically we get p-type and n-type semiconductor materials, and eventually for the construction of the electronic devices we combine them. P-type and n-type semiconductor materials are combined, and that actually results in the making of the electronic devices. So we will see later on in the third chapter that how we actually combine them, and finally we will get the actual semiconductor devices. Okay, so before that we have to make the p-type and the n-type semiconductor materials. Okay, so this I have explained you already that the n-type materials, okay, so the majority carriers are electrons. In the p-type material the majority carriers are the holes. Okay, and we know that if you supply some external energy, okay, the flow of the electrons and the hole will be opposite. Okay, the electrons will be attracted towards the positive charge, okay, towards this one, and the holes, okay, the positive charge will be attracted towards the negative charge. The hole will flowing towards opposite side. So the flow of the electrons and the hole is opposite sides. Okay, so the last thing is, like if we are talking about the thermal equilibrium means we are not supplying any external energy. Okay, like in any form, for example heat energy or in any other things, if we are not supplying that, then the product of the free negative and positive concentration is constant. Okay, so for example let's say n is representing the concentration of the free electrons in a semiconductor material, and p is representing concentration of holes or positive charges. Okay, and if we multiply both of them we will get the Ni square. So Ni is intrinsic carrier concentration. Intrinsic means pure carrier concentration. Okay, so this is actually called mass action law, that under thermal equilibrium no supply of external energy, okay, the product of the free electrons concentration and the hole concentration will be equal to the square of the intrinsic carrier concentration. This is very important relationship, and it will be used later on in the next chapter. That is the end of this chapter. Thank you very much for your attention, and we will discuss more with the examples in the live session. Thank you very much.